Today I'd like to look at an integration technique called partial fractions. Actually, it's just an algebra technique that allows us to rewrite the integrand. And this is the idea. In algebra, we took stuff like this and added it together, got a common denominator, combined it all up. And what we're going to be interested in for the purposes of integration is breaking it apart. So we would have done something like, we would have got a common denominator here. The two factors together would be the common denominator. So this one needs to be multiplied by x minus 4 and this one by x plus 1. So you'd have 3 times x minus 4 minus 2 times x plus 1, and all of that over x plus 1 times x minus 4. Right? That's what we would have done in algebra. And if we simplify that, we have 3x minus 2x or x, negative 12 minus 2, so minus 14 over x squared minus 3x minus 4. So here's the idea. If we were given this as an integral, there's nothing we know so far that would allow us to integrate that. It's the derivative of the bottom is not the top, so u sub's not going to work. It doesn't look like any of those binomial forms from trig sub. It doesn't have trig functions in it, so none of those identity techniques work. So we're kind of stuck at this point. But if we could reverse this process, if we knew how that breaks back apart as this, that thing we do know how to integrate. It's really a linear u sub, right? This is like 3 over u and 2 over a different u. But in both cases, it's a linear u sub, which makes it easy. You just divide by the coefficient on x, which is 1 in both cases. So we have something like this. So the question is, how do we figure that out? How do we start with something like this and know that it breaks apart into these two? And so that's what I want to look at today. So first of all, given this integral, how would we know that that's even a thing to try? Well, if we back this process up, it really goes back to this factoring. So if you've got a rational expression, and remember what it means to be a rational expression, a polynomial on top, polynomial on bottom. So if you have something like that and this polynomial on the bottom factors, then this is the technique that we're going to use. This partial fraction decomposition is what it's called. So let's see how we might figure out how something like that breaks up. So if we were given this, the first thing we would notice is, oh yeah, I know how to factor that polynomial. It factors as x plus 1, x minus 4. So the idea then x minus 14 there. So the question we have to answer is, we know from algebra that we should be able to break that apart. We just don't know what those numbers on top need to be, right? So that's what we need to figure out. So we're going to solve this algebra problem to figure out how that would break up to be that. Okay, so from algebra, we know that the first thing you want to do is get rid of all these fractions. So you multiply both sides of the equation by the common denominator. And the common denominator is easy because whatever's on this side, all those factors are also on this side. So really that denominator there is the common denominator. So if I multiply both sides by this common denominator, it's going to cancel it off over here. And I'll just have x minus 14. But over here, I'm going to have, when I distribute it through here, the x plus 1 will cancel, leaving me the x minus 4. And on b, the x minus 4's cancel, leaving me the x plus 1. Okay. Now, it seems like we shouldn't be able to solve this because we've got actually three unknowns, x, a, b, and only one equation. But x really isn't an unknown here because what we're saying is this expression should be true for all x's. The left-hand and right-hand side should be equal. What we're really trying to solve for is a and b. So first of all, there's really only two things we're solving for. X can be anything. We're not trying to figure out what x is. But we have a polynomial on both sides. And we know that a polynomial, this polynomial needs to be equal to this polynomial for all x. This is what we call an identity. So the only way that's possible is if they're the same polynomial. So let's write the right-hand side in a standard polynomial form. We have x minus 14 over here. What do we have for x's on the right? A times x, b times x. So we've got an ax and a bx, or a plus bx. And then for our constants, our non-x stuff, we've got an a times negative 4 and a b times 1. So the constants are negative 4a plus b. Now, since this is an identity, the left and right-hand side should be the same polynomial. The x term over here has a coefficient of 1. The x term over here has a coefficient of a plus b. So those must be the same thing. So a plus b has to be 1. And on this side, the constant is minus 14. And on this side, the constant is minus 4a plus b. So those must be equal. So minus 4a plus b equals negative 14. We call that matching coefficients. If you've got a polynomial on one side and polynomial on the other, the only way that they're equal to each other is if they have the same coefficients. Well, now we have two equations, two unknowns. And as we know from algebra, we can solve that. Do whatever technique you like best, substitution, elimination. I like elimination best, so I'm going to subtract to cancel those b's. So a minus a minus 4a would be 5a. And 1 minus a minus 14 would be 15. Dividing, I get a is 3. Go back to my original equation. A plus b should be 1, so 3 plus b should be 1. So b is negative 2. So a is 3 over x plus 1. B is negative 2 over x minus 4, which we know we're right because we started with that in the first place. So this would tell us, if we started with this, we would do this sort of as a side problem, a little algebra problem to try and figure out how it breaks apart. Then we would return to the integral and put that in. 3 over x plus 1, negative 2 over x minus 4, and then we could integrate. So the key to recognizing that this is even something that you should try is the fact that A, it's a rational expression, and B, the bottom there, factors. Now, this particular example had very specific types of factors. These are linear factors, right? X is to the first power, x is to the first power. So these are linear factors, and they're not repeated. It's not an x plus 1 and an x plus 1. So depending on those factors, we have different approaches. It's generally the same idea, but this initial setup will change a little bit. So we will look at, what do you do if you have repeated factors? What do you do if these are quadratic irreducible factors? What do you do if you have repeated quadratic irreducible factors? So we'll look at all those cases. The general algebra we're doing here as far as matching coefficients is the same. What's going to change is that first step there of what your initial setup looks like. So we'll look at those next time.